Mm-hmm. So first of all, Wei Chen noticed a mistake I made a couple of weeks ago, so I must apologize. And it was while constructing projective smooth curves, like we had a field K of rational functions, and C was the set of all DVRs in K, say R, such that fraction field of R is K, and then we had another curve S, not necessarily smooth projective, but affine, such that it had the same field of fractions. So there was a canonical embedding J from S into V, and we had to prove that it is an open embedding, that is the complement is finite. And I thoughtlessly copied an argument from Kempf that had a gap, and Wei Chen explained that it had a gap and a correct argument. So the correct argument is that so S is already an algebraic curve. So we know that the ring of functions K of regular functions is finitely generated. So S is the spectrum of some algebra A, and A is generated by, say, F1 and so on, Fn, and then we know that the points of C are DVRs, and A lies in some DVR RC, if and only if all the generators do. Okay, and so it suffices to check that for any I, Fi does not lie in RC for finitely many C. Okay, and this is clear. So we argued this while proving this statement. So namely, Fi does not lie in RC if 1 over Fi has 0 at C, but there are just finitely many such zeros. Okay, so this was a correction of my mistake.
Проблема прошлого доказательства.
Then I claimed that the complement C minus J of S was contained somewhere, but in fact it is the opposite. It is not contained somewhere, but something is contained in it. It's just some stupid thing. Okay. Pardon me?
Спасибо, понял.
Welcome. So now we are back to higher cohomology, higher derived direct images, last time we proved that for any morphism from one algebraic variety to another, and F quasi-coherent sheaf on X, the higher direct images of this quasi-coherent sheaf were quasi-coherent sheaves on Y, and in fact something stronger holds true, and we will prove some very particular case of this stronger statement later on today. So if pi is a projective, or more generally proper, and F is coherent as opposed to quasi-coherent, then all the higher direct images are also coherent. Just a very particular case says that if X by itself is projective, so its morphism to a point is projective, then all the higher cohomology with coefficients in a coherent sheaf are finite dimensional. Okay, and we will prove this today for X a curve. Okay, and already this proof for a curve will be rather involved, and for higher dimension it's much more involved. So it's really an important deep theory. Okay, so let's start, and we will need some sort of obvious but technically important lemma that is essentially an application of projection formula. So we start with two varieties, but there's no morphism between them, and there is a sheaf, quasi-coherent sheaf on one of them, and we have the product X times Y and two projections onto X and onto Y, like this, and we have then we claim that for any higher direct image there is an isomorphism from the cohomology of Y with coefficient in this sheaf tensored over the base field with the structure sheaf on X. There's an isomorphism with the higher direct image of the sheaf F pulled back to X. So like this. Okay, so somehow intuitively this is clear, I would hope, because our sheaf is well, I cannot say constant because it's coherent, but it is so to say independent of X. Yeah, it's pulled back from Y, so it's well, I don't know how to say instead of constant, but independent of a point in X. And that's what is written in the claim of Lemma, right? That all the fibers at the points of X are the same, and they're all equal to the cohomology of Y. And that's very natural to expect. But let's actually prove it. So first of all, we have to construct this this isomorphism. Well, let us call it A maybe. So A comes from the natural fullback morphism from cohomology of Y into cohomology of the product with coefficients in the pullback of our sheaf, and then to the global sections of X with coefficients in the higher direct image. Sorry, like this. So if you remember, the higher direct image is a sheaf associated to a pre-sheaf that measures the whose sections over open subset are cohomology of its pre-image, right? And what I have in the middle term is the global sections of this sheaf. Okay, so there is this natural second morphism, and well, this is so to say the construction of this morphism A on the constant sections, and then I just tensor it by OX. By the structure sheet. Okay, so this is our morphism. We have to check that this is an isomorphism, and clearly this is a local claim. The question, the problem, is local along X, so can assume that X is affine. Okay, and now this is a helpful assumption because we know that the higher direct images are quasi-coherent, and for affine varieties, quasi-coherent sheaves are reconstructed by their global sections, and so we can check on the global sections. Okay, this is strange argument. We well, we reduce our problem to a local statement, but then this local statement we reduce to a global statement and check it globally. Rather strange logic. Okay, so by the quasi-Koch property of this sheaf, we know that the morphism from cohomology of Y with coefficients in F tensored by global functions on X, regular functions, into the morphism to cohomology of the product with coefficients in the pullback.
Какое вот здесь мы явно свойство используем, чтобы вот эти, ну, чтобы эта стрелочка была изоморфизмом?
The last arrow, which arrow you refer to?
Да, вот эта последняя стрелочка, почему она изоморфизм?
No, we have to prove this. So we reduced our initial statement to some local problem, and this local problem to global problem, and this is what we have to prove. So we need to check that this is an isomorphism. Okay. For quasi-coherent sheaves, it's enough on an affine variety. It's enough to check that they are isomorphic. It's enough to check it on the global section. Okay. So this is what we're proving. But now, since X is affine, the projection to Y is an affine morphism. And hence, the cohomology of the product with coefficient in the pullback of F are the same as cohomology of Y with coefficients in the push forward of this pullback. Okay, I mean, we proved such a statement last time, and we only have to compute this latter cohomology. But we know what by projection formula, we know what is the argument. So push F, as we discussed last week, it is just the initial sheaf F, tensor the push pull of the
Можно
structure.
спросить по этой формуле?
Yes. Yes.
Если F у нас квазикогерентный, то F представляется для какого-то, ну, есть соответствующая M, локализация которого даст F.
Yes.
У нас была формула, что
But
вместо F подставить...
Yeah, we don't assume that Y is affine. But if Y were affine, then certainly it would be so, yes.
Если вместо F поставить M с волной, то получится...
If Y is affine. But Y is not assumed to be affine. Yeah, the question is global in Y. So we cannot assume that Y is affine. You cannot do this. We only can assume that X is affine, but not Y.
Понятно, понятно. А локализация не нужна вот этого тензорного произведения?
So I mean, this tensor product is over OY. If that's what you are asking.
Хорошо, спасибо.
And now since this projection to Y is just a projection from a direct product, then we know what is this. This is just F tensor over K with the ring of functions, regular functions on X. Okay, and that's it. So this is just, well, how to say it? It does not depend on Y at all, right? So the cohomology of Y with coefficients in F tensor K something else, doesn't matter what I write here. Any module, any vector space. It's an infinite dimensional vector space, but doesn't matter. It's the cohomology of Y with coefficients in F tensor over K with K of X. Okay, so we are done. And it was a rather stupid lemma, but we will use it as a technical tool in a very elegant computation for curves. So now we move back to curves for cohomology of coherent sheaves, or quasi-coherent on curves. But I must be very careful in order not to solve your current home assignment. Okay, so I'll try to do my best. And we start with F, say, coherent sheaf. But I will know that F is the direct sum of some torsion sheaf plus some locally free sheaf. And the torsion part has no higher cohomology because it's direct sum of skyscrapers. It's a flabby sheaf. So any positive.
Почему он вялый получается?
Since it's a direct sum of skyscrapers, and any skyscraper is flabby by okay, so it suffices to, if we are interested in higher cohomology, it suffices to consider only locally free part. So we assume that F is locally free, and then it means that F is embedded into its rational sections localized sheaf, and in the quotient we get the principal part. Yeah, we discussed this last week while discussing Cousin problem. Okay, and now notice that this big constant quasi-coherent sheaf is flabby. As well as the sheaf of principal parts. The sheaf of principal parts is just torsion sheaf, right? So there is no wonder it is flabby. But the sheaf of rational sections is by no means torsion, and it's constant. But because it's constant, it's flabby. Very counterintuitive situation. So once again, let me write that rational section is flabby since it is constant. So we have, well, let me denote it by, say, G. We have global sections of G surject onto sections of, well, CG on any open set U, just because they are equal. It's a constant sheaf, and so there's an isomorphism, a particular surjection. Since any open subset U in C is connected. Okay, so I'm saying some trivialities, but they have grave consequences. Yeah, so in particular, well, maybe let me write it as a remark. It implies that the higher cohomology, in fact, of any algebraic variety with coefficients in a constant sheaf G vanish for I positive and G constant. Okay, since any Zariski open of an irreducible variety is connected. And hence, the constant sheaf is flabby. Okay, so on the one hand, it's trivial observation. On the other hand, it's very, very bad, because maybe you've heard that in the classical topology, not Zariski, but if you consider complex algebraic varieties, you can equip it with the classical topology, where you have many more open subsets, and you have arbitrarily small open subsets that do not intersect. There are many non-connected open subsets, and you can compute the cohomology of the constant sheaf, say with stock complex numbers, or just say rational numbers. Okay, the constant rational sheaf, and you can compute its cohomology, and it will be equal to the usual singular cohomology of the underlying complex variety. I hope you heard about this, and well, it's an interesting theorem, but not very difficult. And now, if you replace the classical topology by Zariski topology, this breaks down. And if you try to compute the cohomology of constant rational sheaf in Zariski topology, you get nothing. You get zero. Okay, as opposed to singular cohomology of underlying space. And this was the problem that people tried to solve like 80 years ago, or maybe 70 years ago, because André Weil formulated some very nice conjectures about number of solutions of some algebraic equations in finite fields. In fact, we will prove these conjectures for curves over finite fields in a month, I hope. But well, in fact, André Weil first proved these conjectures for curves in 40s, and in early 40s, and then in late 40s he formulated these conjectures for arbitrary dimension, and he himself noticed that the proof would follow pretty formally from the existence of cohomology theory parallel to the usual singular cohomology of complex algebraic varieties. Okay, but then it was immediately clear that in Zariski topology there was no such cohomology theory, and it took Grothendieck and his school to develop Étale cohomology to replace this coherent cohomology, and to prove Weil conjectures in 60s and 70s. Okay, so this was a long aside. Pardon me?
Yeah, do you prove in Bombieri?
I cannot really hear you. There are some connection problems. The sound is distorted. Can you repeat your question?
Yeah, do you prove with Bombieri's proof?
Do I what?
Bombieri's proof?
I missed the verb. Do I what Bombieri's proof?
Oh, do you Bombieri's proof of Weil conjecture?
I cannot still I cannot hear your verb. Just one word. Bombieri proof of Weil conjecture. Do I what?
Are you going to prove, like, which proof are you going to present of Weil conjecture?
The one in Kempf's book.
Oh, I see.
It's essentially André Weil's own proof. Okay. So where were we? I said that the constant quasi-coherent sheaf of rational sections of F is flabby, as well as the sheaf of principal parts of F. Okay, and so this three-term exact sequence just is a flabby resolution of my original torsion-free sheaf F. Okay, Let me write this. This thing is a Fleby resolution of F. Okay, and so we can compute cohomology of F using this Fleby resolution. With last time I explained that there is some canonical Fleby resolution constructed from the discrete sections. Sorry, discontinuous sections. But this one is infinitely well. It's an infinite resolution. It never stops. And for curves, we just have two-term Fleby resolution, and hence there are no cohomology higher than the first cohomology. Okay, so the corollary is for any coherent sheaf F on a curve, projective curve, cohomology with degree higher than 1 vanish absolutely, and we only have zeroth cohomology, global sections, and first cohomology. And now let's formulate the very, very important Riemann-Roch theorem. For curves. So first of all, well, our C is a projective, smooth projective curve. And F torsion-free, so it's a locally free coherent sheaf. So then the cohomology are finite dimensional. Well, we know this about H0, but it's claimed about H1. And in the beginning of today's class, I mentioned that there's a very particular case of the general theorem that higher direct images of coherent sheaves under projective morphism are also coherent. And then we can define the Euler characteristic. This is the difference of these dimensions. Okay, so it's claimed that the Euler characteristic of F is the degree of some invertible sheaf. This invertible sheaf is the determinant of F. Well, I will recall the meaning of these words in a minute. And then there is another summand, namely it's the rank of F times 1 minus G. And here G is the genus of our curve C, and it is defined as the dimension of the first cohomology of the structure sheaf. Okay, so for example, the genus of projective line is 0, and the genus of elliptic curve is 1. Okay, and as for the determinant, say if rank f is n, then the determinant of f, by definition, is the top exterior power of f. Yes.
Пожалуйста, напомните степени дивизора, ну, степень детерминанта f. Это что?
It's an invertible sheaf. Say, let's call it L. And then we know that any invertible sheaf L is necessarily of the form OC of some divisor. Namely, we choose any rational section of L, and then take divisor of its zeros minus divisor of its poles. Okay. And the degree.
У нас всегда детерминант f обратимый пучок?
Yes, by the very definition.
Это почему? Откуда это следует? Он обратимый.
It follows directly from definition, because the top exterior power of any vector space is one-dimensional vector space. The degree of L is defined as the degree of this divisor, and we proved an important theorem a week ago that that this is well defined. I mean, there are many divisors giving rise to the same isomorphism class of invertible sheaf. But they are all the same modular principal divisors, modular the divisors of function. But the divisor of any function has degree 0. So all these divisors have the same degree. Okay.
Спасибо.
Welcome. Okay. So I hope we now completed the statement of Riemann-Roch theorem. It's a very, very, very important theorem for curves. Essentially, whatever we will be able to do for curves will follow from all the calculations for curves will follow from this Riemann-Roch theorem. Okay, so let's start proving it. But the proof will be rather involved and elegant. And I mean, the hardest point is the finite dimensionality of first cohomology. Okay, it's essentially everything else is more or less straightforward, but it's hard to prove that the first cohomology is finite dimensional. Maybe let me write it down. Okay, so we'll do a few reductions, and it will immediately follow that it's enough to prove this finite dimensionality for just one sheaf, for any sheaf at all. So if you know it just for one sheaf, you know it for any sheaf. But for once again, it's hard to prove for any sheaf at all. So well, first part of the proof is a reduction to the case when f is invertible, so rank 1. And to this end, recall we proved the theorem a couple of weeks ago that any locally free sheaf has a complete flag with successive quotients of rank 1, invertible sheaf. Any f has a filtration with successive quotient invertible. Okay, and well, now we proceed by induction. Say, let's assume that we have a section like we have an exact sequence like this. This is invertible. This is our f. This is some quotient. So it has rank g equal to rank f minus 1, and this is invertible. And while we write a long exact sequence of cohomology, 0 to h0 with coefficients in L, to h0 with coefficients in F, to h0 with coefficients in G, to h1 with coefficients in L, to h1 with coefficients, oops, sorry, F, to h1 with coefficients in G, and then we're done because there is no h2. We know it stops here, and so you see from here that if h0 with coefficients in L and with coefficients in G are finite dimensional, then h0 with coefficients in F are as well, and the same for h1. Okay, and moreover, so again, it's proved by induction in rank, right? If we know it for line bundles, for invertible sheaves, we know it for arbitrary rank locally free sheaves. And there was numerical part 2 in our Riemann-Roch theorem. Yeah, the part A was that cohomology was finite dimensional, and then we could define this Euler characteristic. And then the claim was that this Euler characteristic can be computed from some basic invariants of our sheaf. And you just know that those basic invariants are additive in F. So first of all, the Euler characteristic is definitely additive in exact sequences. And the right-hand side of B is additive as well. Just let's have a look at it. It is degree of determinant plus rank times something. So this something is fixed and independent of our sheaves, right? So rank is clearly additive. The only question is about the degree of determinant. Let's see this. Rank F is additive. And the determinant of F is the determinant of L tensor determinant of G. Hence, the degree of determinant of F is the degree of determinant of L, then plus degree of determinant of G. Okay, so we are done with this. We reduced our Riemann-Roch problem to the case of invertible sheaves. Okay.
Базу индукции мы для пункта A очевидно.
No. The base is not obvious at all. The base is this statement for invertible sheaves, and now we have to prove this. So the base of induction is the Riemann-Roch problem for invertible sheaves. And well, we turn to this problem. Okay. So the second step is establishing Riemann-Roch for invertible sheaves. But now, as I claimed before, it suffices to produce just one invertible sheaf such that the dimension of its first cohomology is finite. Let me argue why this is so. So we take any invertible sheaf and take any point in our curve and consider a short exact sequence. So in the quotient you get a skyscraper sheaf, just one-dimensional vector space at point C. Okay, and it gives rise to long exact sequence of cohomology.
Почему такая короткая точная последовательность является короткой точной последовательностью?
Well, first of all, we already used it many times, but then I would say it's obvious. Yeah. Well, by the very construction, away from point C, there is no difference from M and M twisted by C. And at point C, you allow sections with first degree, well, first order poles at C. And there is only one such section, modular regular section. So well, it's just obvious, I would say. Okay. So we have global sections with coefficients in M, then global sections with coefficients in the twisted sheaf, then global sections with this coefficients with this skyscraper, then first cohomology with coefficients in M, then first cohomology with coefficients in the twisted sheaf, and then nothing because the skyscraper sheaf has no higher cohomology. And well, we know that this guy has dimension 1. Okay, so it follows that the dimension of first cohomology of M is finite if and only if the dimension of first cohomology with coefficients in M is finite, and they differ. Well, no, not they, but the Euler characteristic differ. Well, if they are both finite, then the Euler characteristic of M of C is the Euler characteristic of M plus 1. Okay, just by the additivity of Euler characteristics in exact sequences. So any invertible sheaf is obtained from any other invertible sheaf. Yeah, we started with saying that it suffices to prove our theorem for just one invertible sheaf L, and then we started considering another invertible sheaf M. Okay, but they are related by some twisting. Namely, I have here some points in our curve minus some other points in our curve. Okay, namely, we just take their ratio. So I M tensor L dual is O of this divisor. Any invertible sheaf is O of some divisor. So we would take the tensor product of M and L dual. It's another invertible sheaf, and it's O of some divisor, and then we have this equality for M and L. Okay, so it follows that just adding or subtracting those points one by one, C's and D's, we get that the Riemann-Roch theorem plus, well, just a second. Well, maybe, sorry. The finite dimensionality of H1 plus Riemann-Roch. So this package for
а вот L дуальная это home L куда? К или в О?
L dual is home from local home from L to O, right? So the same package for L, okay, as I claimed in the beginning, okay, and there we are. So remember, we wanted to prove that our theorem must be checked just for one invertible sheaf. Okay, for any one invertible sheaf, then it will follow for any other invertible sheaf, and that's what we just did.
Он же L определяется однозначно пучком F изначально. Он же не какой-то произвольный, а у нас есть изначально пучок F, и мы по нему строим L.
No. First we reduced this Riemann-Roch package for arbitrary locally free sheaf F to just rank 1, to invertible sheaves. This was the first part of the proof, right? We reduced the statement for arbitrary locally free sheaf to rank 1. Okay, now for rank 1, I claim that the statements for just one invertible sheaf are equivalent to the statements for any other invertible sheaf. So it suffices to prove it for just one invertible sheaf. That's what we achieved so far, just by adding, subtracting. Points C, I, D, J, one by one.
But then we add them, subtract them, and in the end we get the structure sheet. But do we know?
Yeah, for example, yes, it's a good idea. Yeah, to reduce it to structure sheet. Yes. Though it's not what we will do, but for example, we could reduce it to structure sheet. Yeah. If you had some mechanism to prove it for structure sheaf, then we would be done, right? And for example, the home assignment, the current home assignment does it for structure sheaf, and in fact for any other invertible sheaf. So in home assignment, there is a solution of this problem for any invertible sheaf. Okay, but I will prove it in some other elegant way. I mean, using the idea of cohomology. In the home assignment, you don't even pronounce this word. But if you are allowed to use cohomology technique, you can do this in an elegant way. And that's what we do now.
Разве для структурного пучка это не очевидно?
So why do you think it's evident for structure sheaf that the first cohomology is finite dimensional? Yes. Why do you think it's
By
evident?
definition, we know that G is a... so it's
yeah,
part of
but
the theory,
G
yes?
is defined modulo the finite dimensionality assumption. So if you already prove part A, then you can define this genus as dimensional first cohomology. But before you proved that finite dimensional, it makes no sense.
Okay.
And I mean, it's really difficult. I mean, even if you do it with classical in analytic situation, then again, it's a difficult claim that the first cohomology of say complex Riemann surface, compact complex Riemann surface has finite cohomology in the classical topology. It's a difficult functional analysis statement. Yeah, it's really a deep thing. You do have to check something. It does not come for free from any point of view. Well, somehow everybody is used to it, but it's a deep theory still. Okay.
Мы использовали где мы использовали, что C проективная кривая?
Well, if your curve is affine, then we will have no first cohomology, as we already proved. Yeah, the quasi-coherent sheaves do not have higher cohomology, but the zeroth cohomology will be infinite dimensional. For example, for structure sheaf, the zeroth cohomology are global sections, and they're just the sheaf of regular functions, the global regular functions. On an affine curve, it's an infinite dimensional ring of global regular functions. Yes, so there will be nothing to speak about. This Euler characteristic will be infinite. You will not be able to compute it. Okay, so finally, let's proceed. Now we'll prove the following lemma, and this is the key point. The key lemma. So assume that the global sections with coefficients in M twisted by the first differentials, Keller differentials. So not M, but M dual, sorry, is zero. But we have control over this, right? Because we know that if our invertible sheaf has negative degree, then it can have no global sections, right? It was an evident claim, but we will use it now. So if M will have a very big degree, then M dual will have a very negative degree, and the degree of M dual twisted by the Kähler differentials will be still negative, and there will be no global sections. Okay, but if this is so, then the first cohomology of M is 0. Okay, in fact, this is a part of Serre duality, and the next time we will prove Serre duality in the complete generality for curves. But today we will need this simple consequence of Serre duality. Okay, so if we know this, just let me write down what I said. Take degree of M very positive, and degree of M dual, very negative, hence degree of M dual tensor omega c negative, hence no global sections.
Да, а какой дивизор определяет омега c?
It doesn't matter. Well, eventually we will study this omega c in all the detail, but it doesn't matter. Whatever this sheaf is, we will see that its degree is 2g minus 2, for example. But it doesn't matter. Whatever is its degree, it's some fixed number, say 1 million. But if you take M of degree bigger than 1 million, then this guy will have negative degree. And so we'll have no first cohomology.
Просто если формально подходить, то омега c это как бы O от минус диагонали. Но там еще нужно факторизовать же по I квадрату.
Right. We'll use this just in 5 minutes. Okay. So,
немножко непонятно, если мы факторизовать еще должны по идеалу обратного идеала в квадрате, то получается там определение.
Just wait 2 minutes, you will see. So, well, and we get the Riemann-Roch package for all locally free sheaves. Okay, so this is the only thing it remains to prove. Okay, this is the last lemma. It proves everything. Okay, so well, if you remember, we had one criterion last Thursday, a week ago, that guaranteed the vanishing of first cohomology. It was for adding, for twisting by points. If when you twist by a point, the global sections increase by the rank of your sheaf, say for a verbal sheaf increase by 1, then there is no first cohomology. So we are going to use the criterion of a week ago that for any how to say it, for any effective divisor D, the dimension of global sections of M twist by D is dimension of global sections of M plus the degree of D. So if you know this statement, then you know that the first cohomology with coefficients M vanish. Okay. So how are we going to use this statement? So we consider this twist for an effective divisor. And then we know that the global sections of our curve with coefficients in the Kähler differentials times F dual is the global sections of C with coefficients in Kähler differentials tensor M dual twisted by negative D. And this is certainly a subspace of global sections of Kähler differentials twisted by M dual. Yeah, these are sections which vanish at the divisor D, but this is 0, so everything here is 0 as well. Okay, so from by our assumption, in the lemma, we know that it is satisfied for the twisted sheaf as well. So now choose a point and consider an exact sequence from 0 to F to twisted sheaf to the skyscraper at this point. Oops, sorry. Okay, and hence we have the co-boundary map. Delta C from the global sections of this skyscraper sheaf to the first cohomology of sheaf F. And the key claim is that this co-boundary map is just 0. And from this key claim, everything will follow. Let me show. So, granted this, we have an exact sequence 0 to first to 0th cohomology of F twisted by an effective divisor to the global sections of F twisted by an effective divisor plus C. Well, okay, just sorry, it was not F. Sorry, it was M. M. Okay, and M of D was F. And just because the co-boundary map is 0, right? So in principle, we could have this co-boundary map here going to the first cohomology, but we know that the co-boundary map is 0. So that's it. And so it follows that the dimension of global sections with coefficient in the twisted sheaf is oh, sorry, maybe I should yeah, this is the dimension of global sections of C with coefficient in MLD plus 1. Okay, and this is the criterion for vanishing of the first cohomology. Okay, so the only thing to check is the vanishing of this coboundary map. Okay, well, let's prove this, and this is where we have to use the definition of Kähler differentials, as Sergei Alyoshin wisely recalled 10 minutes ago. The proof of the key claim. And also we will use here this technical statement we proved in the beginning of the class. Okay, so we'll deduce it from a global statement as our point varies in our curve. So consider the square of our curve, and there is the first projection to one copy and the second projection to another copy, and then we have the following exact sequence. F to the twist by diagonal, and this twist by diagonal is a global analog of twisting by the point. If this point varies in the curve, globally you obtain twisting by diagonal, and in the quotient you get the restriction to diagonal. Okay, and then we push forward to the second copy. And consider the coboundary map. But now it does not depend on a choice of a point. It varies. So it'll be the second. The direct image with respect to the second projection over the pullback with respect to first projection of F, twist by diagonal, restricted to the diagonal, and here you go to the first direct image of the pullback over F, and by this technical claim in the beginning of our class, this is nothing but the first cohomology of our original sheaf, tensored over this, tensored with the structure sheaf of C. Okay, by the first technical lemma today. Okay, so we have to compute this co-boundary map. So our delta C is the fiber of delta over one particular point.
Почему это так?
Pardon me?
Почему это так?
Just because nothing happens along C, it's so to say constant along C. Yeah, just the diagonal itself is another copy of C, and nothing happens along C. And it suffices to check that delta is identically 0. Then all its fibers will be 0. And now what do we know? We know that now is the well, the apotheosis of the argument. It's what Sergey asked before. So we know that if we take the structure sheaf of the square and take the ideal of the diagonal, and then take the quotient modulates square, then we get the sheaf of Kähler differentials by definition.
Извините, а дек омега С это будет дек минус дельта?
The degree of this Kähler differential sheaf, that's what you asked?
Да-да, степень омега С.
It is 2g minus 2, and we will prove this next time, but we don't need nor use it today. It is some number, but we don't need to know that it's 2g minus 2.
Не-не, у меня проще вопрос. По определению степень омега С это будет степень дивизора минус дельта?
First of all, in Russian you say divisor.
Дивизор, извините.
And then, no. The structure sheaf of C squared twisted by diagonal is something on the surface C squared, and we don't use no numerics about this surface. We know how to define degree of a sheaf on a curve. We don't know anything about surfaces. We don't use anything about surfaces, except for definition of these Kähler differentials. The Kähler differentials are just defined this way. Okay.
А что такое тогда по определению степени пучка омега С?
Any invertible sheaf on a curve has a degree, which we discussed already today. So maybe let's not discuss it anymore. You choose a divisor such that the sheaf is O of D, and then the degree is defined as the degree of this D.
Просто здесь вот равенство ровно то и написано, что вы говорите. Вот мы находим О от дивизора какого-то, дивизора.
No, because this is about surfaces. In the left-hand side, you have something on a surface.
Ну хорошо, извините, понял.
Okay. So this is by definition, and hence just dualizing. We get that the omega C dual is the structure sheaf on the surface C squared with poles on delta restricted to the diagonal, and hence the push forward of the pullback of our sheaf F with poles on the diagonal restricted to diagonal is just F tensor the inverse, well, the dual, sorry, the dual of Kähler differentials. Okay, just because the projection identifies our diagonal with the curve C. Okay, and it's an isomorphism, and nothing happens for per one pullback. Okay, so now we have our co-boundary map delta from F tensor the dual of Kähler differentials to the first cohomology. Sorry, of F tensor the structure sheaf of C, and this is dual to the first cohomology. Sorry, with coefficients in F dual tensor OC to the Kähler differentials tensor F dual. Okay, but there is a coefficient space, the first cohomology tensor OC, and apart from this possibly big coefficient space, we're speaking just about global sections, right? From OC to omega C tensor F dual. But we assumed that there are no global sections like this. From omega C to differential tensor F dual is 0. Okay, hence delta dual is 0, and hence delta is 0, and we are done. Okay, this was a rather elaborate but elegant argument, and we proved the vanishing of first cohomology in some examples, so it's finite dimensional always. That's it. Thank you for today. Next time we'll derive many nice corollaries from the Riemann-Roch theorem, and we'll also prove the Serre duality theorem. It will be essentially a version of today's argument. I mean, the Serre duality will be a version of today's argument. Well, today we proved, in fact, some particular case of Serre duality, and we'll prove the general case next time.
Можно вопрос?
Yes.
Вот вроде середины февраля пока что не планируется офлайн лекции.
Well, the problem is it's my health problem.
Okay.
I fractured my ankle, and I'm still unable to walk, and I will be unable for at least 1 month more. I apologize for this. So I'm just physically unable to use a blackboard. Sorry about this.
Okay, I understand.
It will continue for at least a month more.
Можно спросить по лекции?
Yes.
Вот я все же не понял, когда мы доказывали теорему Рiemann-Роха, вот во второй части мы сказали, что можно свести доказательство к произвольному пучку L. Вот почему это так случилось? Вот произвольность откуда возникла?
Well, I argued that for the statement for any invertible sheaf M is equivalent to its statement for a twisted sheaf M twisted by a point, twisted or untwisted by a point. And then any invertible sheaf is equivalent to any other invertible sheaf by this operation of twisting or untwisting by points of a curve, of our curve.
Понял, спасибо. И вот еще вопрос.
Yes.
А как вот представить вот пучок рад f рациональных сечений
Yes.
Через копредел?
Well, first you take rational sections. What does it mean? You take smaller and smaller and smaller open sets. So you throw away more and more and more points from your curve. Yes, and you have bigger and bigger and bigger space of rational sections with poles at those points. So you have a union of those increasing sequence of spaces of rational sections, regular over smaller and smaller and smaller open set. And then
Цепочка вложенных.
Yes, yes. And then you just take a constant sheaf with this coefficient.
А мы разве не получим росток в результате?
But where? Well, it is actually the stock at the so-called generic point of our curve. But we didn't yet introduce generic points. We only considered maximal spectra. And we need some more advanced notion of spectra to have generic points. We'll do this in late March, but so far we are staying on some elementary level.
Okay, and I also have a question.
Yes.
Can you please recall, are there any examples of neither projective nor affine curves?
No. We almost proved this, and in your current home assignment, there is the statement exactly like what you asked. So if you take a projective curve and remove just one point, any point, then the resulting curve is necessarily affine.
But given an arbitrary curve, how can I understand that it is projective or affine?
I don't really understand your question. If there are non-constant functions, it is affine. If all the regular functions are just constants, it's projective. For example, does it satisfy you?
How do we prove this?
Well, okay. If you want, we will give a proof next time. But it is also a problem of your home assignment. So it's up to you to prove this.
Okay. I will look through it. Thank you.
Okay. Okay. So then I'm saving the note, crossing my fingers. Hopefully, it will succeed. And then I'm saying goodbye.
До свидания, спасибо.
Welcome.